Hello, everyone, and today we are going to continue our series of lectures, lecture number 7, where we are going to talk about three special types of matrices: diagonal, triangular, and symmetric matrices. I'm going to start with very short definitions, which I'm going to just give as examples. So what is going to be diagonal matrix? Diagonal matrix, we are going to use letter D for that, is going to have numbers or elements or non-zero elements only on diagonal. All other elements must be zero. It does not mean that you cannot have zeros on diagonal, but other elements must be zeros and diagonal can be zeros or non-zeros. Second type is called triangular matrix. Triangular matrix is going to look like we have zeros all below the diagonal. These are zeros, right? And above the diagonal, you can have zeros or non-zeros. Matrix like this is called upper triangular, and we use letter U for that. If you have zeros above and non-zeros or possible non-zeros below, we are going to call it lower triangular matrix. So essential elements in the bottom, and here essential elements in the top. And the last type of matrices we are going to learn is symmetric matrix. Symmetric matrix is going to have symmetry over main diagonal. Symmetry means that, for example, if you have number 4 here, it's going to be the same number here. 4 or 5 here is going to be same 5, and 6 here is going to have same over here. Mathematically, it's going to look like matrix A is going to be equal matrix A transpose. So if you take transpose of the matrix, which you remember exchanges row and columns, you're going to get the very same matrix. So this is that's the definition, and this is example. Well, I'm going to say maybe few facts about like diagonal, triangular, symmetric matrices, couple of theorems. My suggestion also to read the book on this section, just because there are lots of like little tiny things about these matrices, which I'm not going to put in the lecture. Well, what is interesting about diagonal matrix? Inverse of diagonal matrix is going to be actually also diagonal, and that's going to consist out of inverse elements. So it's one, I'm sorry, 1 over 1, 0, 0. 1 over 2, 0, 0, 0, 0, 1. For this specific one, 1, sorry, 1, come on, 1 over 3. Well, we can literally check it by multiplying d by d inverse and get identity. Well, it's going to be interesting that all diagonal matrices, if you multiply them, they are going to give you another diagonal matrix. For example, if I multiply diagonal matrix by itself, which is going to be diagonal matrix square, it's going to be just a square of diagonal elements. 2 square, so 3 square. And again, you can just literally do the multiplication. The only specific thing about diagonal matrix, it has only I elements. So elements 1, 1, 2, 2, 3, 3. And when you do multiplication, only those elements are going to be present in the final product. Okay? So that's all about diagonal matrices. We are going to have them sometimes, but there are not like many things we want to know about them. Triangular matrices. What is interesting about them? Well, the first fact about triangular matrix is that if you take upper triangular matrix and do transpose of it, you are going to have lower triangular matrix. Well, let's imagine that you do transpose of this specific one. So the row 1, 2, 3 is going to become column 1, 2, 3. Well, in this one, this L has 1, 2, 4, just because my example was looking like this, but it's going to have the column, and next row is going to become column, and next row is going to become column, and eventually we are going to have all these zeros on the top. Well, you can try to prove it, or by yourself. Maybe it's going to you will understand a little bit better if you explain it or visualize it by yourself. Fact number 2. I'm not going to prove both of them, but I'm going to just say that if you have 2 upper triangular matrices and you multiply them, the result is also going to be upper triangular matrix. So it's not going to be random matrix, and it's going to be diagonal or lower triangular. It's going to become upper triangular again. Why does it happen? Well, I don't wanna really prove it like a theorem, but I wanna kind of draw the picture. I'm going to draw the first matrix like this. That's going to be the second matrix, and I'm just going to talk about like I'm going to draw circles for non-zero elements. Remember, they are usually going to happen on diagonal. So something like this are non-zeros and zeros, zeros, zeros everywhere. In the second matrix, U2 is going to have also non-zero elements above the diagonal and zeros, 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 zeros. Okay, so they both are upper triangular. Now, I'm going to start multiplying them. Remember that multiplication will take row multiplied by a column. And as you probably see, this column is going to have all zeros below the first element. So basically it's going to be just the first element. I'm going to graph it like this. Now, if I take second row and multiply it by the first column, what is going to happen? In the first column, we have element only on position 1. And here, we have exactly 0 there. And the rest of the elements here are non-zero, but they correspond to zeros. And when you do this multiplication, it's going to be non-zero element by 0 and non-zero elements from this row by 0 elements of column. And that's going to produce 0. All other rows are going to have same. There are two zeros, and one of them is going to multiply by non-zero element and another by 0 element, and the rest non-zero elements from here are going to be multiplied by 0 and 0 again. And you can repeat this process for every row and column. Just for this one, we have two elements here, and starting with a second row, we are going to have again zeros, zeros, zeros below. And the second row is just like if you starting with the third row, we are going to have all zeros. So second row is going to have something, and the third row is going to have 0, 0, and so on. And it's going to be just the same pattern. So we are going to get upper triangular matrix again. Okay. So what else we need to know? Now, guys, I'm going to concentrate on symmetric matrices and kind of have several theorems about them. So now I'm going to move to symmetric matrices. First, the theorem is going to sound like this. There are going to be like more theorems about symmetric matrices, so I'm going to put them in underneath. So theorem number 1. If the product of two matrices is symmetric, it's going to mean that AB equals BA. So what is the meaning of this theorem? You know, guys, that usually when we multiply two matrices and we switch position, we're not going to get the same product. Lots of these products won't even exist. So that's very interesting that if you have a product of two matrices and that product is symmetric, then these two matrices are going to commute. So you can exchange position and you are going to get the very same. I'm going to prove it. You see that I have arrow in two directions, which means that this is equivalent statement. So this hypothesis followed by conclusion. And if you go from conclusion, you will be able to prove the hypothesis. So basically, this is two equivalent statements. I'm going to prove them. Okay, I'm going to prove them by kind of doing different directions. So that's a proof of this direction. So from symmetric follows that I can switch them. Okay, so given A, B equals A, B transpose. That's what is given, because symmetric means that the matrix, which is a product of two other matrices, is equal to its transpose. Now, guys, what I'm going to do, I'm going to work on my right side. I'm going to continue working. So I'm going to distribute this transpose over both matrices. Remember how it works. You have to switch position. And guys, I forgot to mention that matrices themselves must be symmetric. How did I miss it? Yeah. Because that was in the beginning of the bigger theorem, which I decided not to prove. But okay, now I'll need to mention because I'm using it actually. So I'm going to probably, I don't know where to insert it. So let's insert it over here. A and B supposed to be symmetric themselves. Yeah, just like in the book, the theorem consists out of like 4 parts. And I decided that first 3 parts are too easy. You can actually understand them or look and prove them by yourself. But the last part is a little bit like tricky. So A and B are symmetric themselves, means that B transpose is equal to B and A transpose equals to A. And I was not supposed to write down transpose here since I already used the theorem. Well, what I have, AB product equals BA. So I actually proved that they commute. Now, opposite direction. Given A, B equals BA. I need to prove that it's symmetric, means that AB equals AB transpose. So I'm going to do, since B and A both symmetric, I'm going to put instead of B transpose, instead of A transpose. A and B symmetric. And after that, I'm going to unify them into AB transpose using the rule that the product of two transposes can be converted into transpose of the product. And basically, it's already the final statement, right? So AB product equals AB transpose means that it's symmetric. Symmetric proved. Okay. Yeah, I'm sorry. That's sometimes I forget stuff. And I'm trying to make shortcuts. Yeah. So guys, we are not going to forget this upper line tells that for A and B symmetric matrices, if the product is symmetric, means that it's commuting, and if it's commuting, then it's symmetric. Okay. Well, we are going to have one more theorem, which is also kind of easy. Theorem number 2. If A is invertible symmetric matrix, then A inverse is also symmetric. Well, you probably can guess that it's going to work like that. I'm going to kind of start my proof by not drawing this, but drawing empty square. So I know that it's invertible symmetric. So what is given? It's given that A equals A transpose and A as A inverse. That's a given. Given. What I'm going to do, guys, I'm going to take the inverse, which I know exists, and I'm going to take transpose of it. I know that by one of the theorems we had when we had transpose matrices introduced, I can switch inverse and transpose over here. So I'm going to do it. I'm going to write down A transpose and over here inverse. We can do switch transpose and inverse. And next, I'm going to use the fact that A transpose is actually A. So I'm going to put A here. Oh. A inverse. So, well, maybe I don't need parentheses. That's parentheses was not a good idea actually, because I'm not giving like something more complicated. Now, guys, what I have, I'm going to use green marker. I have matrix A inverse, and we have matrix A inverse transpose, and they are equal to each other. That means that A inverse of matrix is symmetric. So I proved my statement. Okay, sometimes proofs are so simple that it's hard to like get. Okay, we already proved it because like two statements written and that's already proved. Well, again, matrix is called symmetric if its transpose equals to it. So for inverse matrix, we have transpose of it and it equals to it. The last theorem is going to deal with just regular matrices. Here, guys, in theorem 1, we were dealing with two symmetric matrices, right? In theorem 2, we were dealing with symmetric and invertible matrices. Theorem 3 is going to deal with arbitrary matrices. So for arbitrary, which is a little bit strange, right? For arbitrary A, product of A by A transpose and product of A transpose by A is symmetric. And here, guys, no conditions on A. A can be even like M by N matrix, arbitrary. I'm going to show this. I'm going to take matrix A and multiply it by matrix A transpose. Guys, I want to talk like, is it possible to do this multiplication? We remember that matrix A has dimensions A, M by N. Transpose is going to have dimension N by M, right? Remember that number of rows and columns is changing. Imagine when we multiply two matrices, the inner dimension disappears, and the resulting matrix, whatever is like here, you don't know, is going to have dimension M by M. So it's going to be a square matrix with dimension M. I'm going to label it C. Now, what I'm going to do is, I'm going to take now this product, A by A transpose, and take a transpose of it. Just check, is it going to be equal to the matrix itself or no? Remember that what transpose is doing. Transpose is distributing to the matrices and switching positions of them. So actually, A transpose. Transpose, the first one comes the last one, and here is going to be A transpose. Transpose applied to this one. Now, transposing two times is going to eliminate any transposing, correct? And this is just transpose. So what we see, guys, we see the matrix A transpose, and we see matrix A transpose. But here we have transpose of it, here we have nothing of it. So basically, from this statement, we have that A transpose equals A T. If we treat it as matrix C, and this is matrix C, we are going to have C transpose equals C, which means that C symmetric, and which is proving this statement that A transpose is symmetric. Yes, I don't want to prove the second part. Second part is proved exactly the same way, just like instead of like A transpose, you write down A transpose, and you just apply everything same, and that's going to be the proof of the second part. Okay, here reminding you that we have arbitrary matrices. And interesting that if you multiply A arbitrary matrix by transpose, the result is going to be a symmetric matrix. Sometimes helpful to know that because symmetric matrices are looking much nicer than just like arbitrary ones. Okay, that's all for section 7. And guys, I want you to kind of read this section. Again, I proved only major theorems, and I did not do lots of examples. And even like the last theorem about transpose of inverse and inverse of transpose, I did not prove it. So you can try to look at it yourself. Okay, that's all for today.